Okay, thank you. Do I use this? Yes, I do. Okay, so our top level objective with Dawn was to go backwards in time and to try and understand the beginning of the solar system by interviewing the earliest participants who were still around. So we went to the two largest bodies in the asteroid belt, Vesta and soon Ceres. In order to get there, we used ion propulsion and to get the needed delta V to get off the Earth with a regular small rocket and then do the navigating we had to do with ion propulsion. We had a small payload. We still have a small payload. We carried camera, visible camera, and visible and IR mapping spectrometer, a gamma ray and neutron spectrometer, and we used radiometric tracking for gravity. The history was that we were selected for development in 2001. We got launched in 2007, arrived in Vesta in July 2011, and we left Vesta in 2012, and now we're going to arrive at Ceres in March of 2015. I know the community is interested in the Discovery mission. This is a Discovery mission, and there'll be a lot of activity. We started working on this back in 1992 when this first Discovery workshop was held. So don't expect every one of you 30 or 50 people who are sending in proposals to get through the first time, but develop a good concept and then keep at it. That's just don't give up. Do a good job, and eventually the mission will get flowing. So what did we know about Vesta when we started off? Well, we knew what its mass was. We knew its size from stellar occultations and HST and adaptive optics. And we knew, or we thought we knew, that the HED meteorites came from Vesta, and then by analyzing the geochemistry of those meteorites, we had an idea of the processes that had gone on and the age of Vesta itself. And we also, with HST, had a rough shape of Vesta. So we made from that a simplistic model. We thought that based on the geochemistry of the HED meteorites, that the iron core would be about 100 kilometers, and that would be surrounded by a mantle of olivine, and outside of that we'd have a eucritic and diagenetic crust. We expected it to be currently inactive, dry, and shaped almost entirely by impact processes. When we made this figure early in the program, I thought to myself, well, we'll never show that. That puts Vesta, which is down at the bottom, in a fairly bad light. That it's tiny and those other big things are active and doing great things. That's almost embarrassing. Let's put that at the bottom of the slide pile. However, Vesta has stood the test of being a small planet. It does have features and processes reminiscent of its older siblings, or larger siblings. They're not older. There is terrain on Vesta that resembles that of Mars, and also a little bit of Mercury. There's tremendous relief on the surface of Vesta relative to its size. The rock is strong, and the processes have built up fairly large topography. Vesta has an older surface in general than those other bodies, and we're trying to see back past the late heavy bombardment. Simone Marchi has made it a little easier for us to do that by diminishing the size of the late highway bombardment, but we're trying to, there still is difficulty in seeing a long way back from just those surface scars. Before we go on, let me say a little bit about how we obtain the data. This is a mapping mission, and we're reaching a body that we really didn't understand very much at all, so we have to go carefully. So our first orbit is that outer orbit there. Whoops, sorry, I didn't. The outer orbit is what we call survey orbit, in which we obtain low-resolution imagery of the entire surface, and then get the gravity data that we need in order to fly the mission. We haven't explored this body before. We don't know what the gravitational field is. We have to navigate in it. So we're moving slowly and carefully. But we also get complete coverage of the surface, so we know what it is that we're going to be looking at in more detail. Then we will go down to the Hamel orbit, the high altitude mapping orbit, and we get a complete surface coverage in all the camera filters and the images we need to do stereo topography. And we get some higher resolution IR and spectrometer data. Finally, we move down to the low altitude mapping orbit, which we call LAMO, and get the gamma ray and neutron data, which really is sensitive to altitude, as well as get our gravity measurements. And we get higher but incomplete camera data and VIR data. Before we left Vesta, because Vesta has obliquity, serious obliquity, that we were waiting for the sun to come up and shine on the North Pole, and we got some data very close, almost up to the North Pole, and got the complete coverage that we needed to make our maps and our stereo topography. And Vesta does have serious stereo topography. On that map, which is, this is topography color-coded, from the deepest blues to the whites is about 40 kilometers. We were surprised by these images of the South Pole because we expected there to be a southern basin, but in fact there were two basins, one the order of 1 billion years old, maybe older, and we named that Rhea Silvia, and then an older basin, a little bit smaller but much older, that also affected the entire surface. So when we looked at the surface, we started, we felt proud of ourselves. If we say here, look at the band depth, the 1 micron reflectance absorption feature in pyroxene and the 2 micron band center, and we plot where the points are that we see in the VIR spectrometer, we see that there's regions that have to be diagonite and have to be eucrite, and then we have regions that agree with the howarditic mixture of the two. So we felt, well, Vesta is how we expected. But and we were glad that we didn't have to overturn our paradigm, because we had been working very solidly with a model of the origin of the solar system, and if we had not found this sort of confirmation, then things would have been topsy-turvy. But that's not to say that there weren't surprises. And First of all, the surface itself was a surprise to us. We had troughs that circled the planet. One is set associated with Venonea, and another set that were associated with Rhea Silvia impact. We had, as I pointed out, large mountains and valleys, but we also had this strange snowman feature here that still puzzles us. It's not just that it looks like a snowman, but the whole region is enigmatic to us. If we look at the color ratios that we can make with our color camera, then we see that the surface is not uniform. It's very diverse. And that tells us that there are very heterogeneous internal processes that have mixed this planet up. It's not that simple model that we had in our minds when we were designing the mission. This model of a magma ocean of olivine is at risk. We just do not see the olivine excavated where we would expect it. The surface is also diverse in black and white too. We have very bright features. We have very dark features. We see regions where there seems to be long flows that of dark material overlain with white material that we looked at by looking at, the piercing by craters and finding these mixtures down below the surface. So it really is puzzling to us, but also exciting at the same time. Now, that some of us think that there is this black material that might be endogenous, but it's also possible that we're not excavating dark material, we're bringing dark material to the surface. And so this one, I would say, looks like an impactor from afar that brought us dark material, but it could be also from inside as well. There's certainly bright materials on the surface that we think are fairly pristine. There's very little space weathering on this body. To quote Tom Accord, the range of albedos is amongst the largest observed in the solar system on rocky bodies. A number of Dawn investigators were looking for volcanism. The closest thing, I mean, not today volcanism, but evidence of the past. And the closest we came is this region, Brumalia Thalis, where this crater Thea on it looks like it may have excavated some different material from the interior. But that other than this particular example, we haven't found any other clear example of possible early volcanism. As I mentioned that we were looking for evidence for a magma ocean, the only place we found olivine was in patches at high latitudes, basically. So that our simple ideas of the internal chemistry was wrong. There might have been plutons, magma chambers. There might have been percolation of the material up and sequestration of materials in different ways than we were thinking. But it's a heterogeneous body. Another paradigm shift is in the wetness. There already had been evidence for water in the meteorite record, but that when we looked at the surface, we saw pits down in the some of the craters, and in fact on the edge of the Marcia crater. And it looks like there's devolatilization. These are not impact craters. So that brings up the question, was there standing water? And is there other evidence that, there's water on Vesta or was water on Vesta? And looking at the crater walls of Marcia and Calpurnia and others, if we look at the gullies, there's some gullies that just look like material slumping down, but there's other gullies that do look like streams of water have been carried down into the crater, and lobes of material down at low altitude, or at the bottom of the crater. So most of us are believers that at one time water was released from the crust. Perhaps there is permafrost in regions of Vesta today. Yeah. Okay. And just to whet your appetite here, that there's a ribbon across the surface. Now, some people are deniers and say that's not a ribbon that extends from way up here down to here, but it sure looks like that to me. And this is the Marcia region up here. So it comes from that enigmatic region that we're puzzling over. So we have not solved all of the puzzles that we have. Now, where is Dawn now? Dawn is on its way to Ceres. It's a lot closer than this diagram makes it look like, because that's where Dawn and Ceres will be next spring. But today, Dawn and Ceres are over here, about something of the order of, say, 5 to 10 times separated as the Earth and the Moon, but getting close. And so we expect to be there on time in March of next year. Now, when we get to Ceres, we expect a density that's going to be much less than that of Vesta, so there's going to be a lot more water, and plumes have been reported arising from its surface, so we will be looking for them. Okay, to conclude, Vesta is a tiny planet. It was clearly undergoing transformation from accreted dust to a differentiated world with the processes that we find on larger planets. We believe that Vesta is a protoplanet and would have, given a chance, develop into quite a bit. But it was a small body, and it cooled and stopped that development. But it's far from a homogeneous blob as we sort of expected it to be. It's got diversity of character and a very interesting surface and structured interior. Water has been important for Vesta and still may be important on Vesta. There may have been transient atmospheres, and as I said, running water may have been present at times. Vesta is bright and it appears fresh. Now, what has kept this high albedo? What has prevented that space weathering? And I conclude that Vesta does deserve the title littlest terrestrial planet. It's intact. It supports many of the processes that we associate with a terrestrial planet. In closing, I'd like to also thank the many people who participated in getting the Dawn mission going and continue to operate it. We're very grateful. And the Smithsonian Institution this year gave Dawn the Current Achievement Award. And there's the flight ops team standing around after the award was presented at the Air and Space Museum in March. Thank you, everybody.
Fascinating results. We have time for a couple of questions. Would anybody like to ask? Okay, yes. Yeah, I've got a question about that ribbon of material you mentioned.
We do too.
I didn't quite catch what was so peculiar about it that made it so notable. Could you elaborate, please?
Well, visually, it's a colored ribbon like we don't see anywhere else on the surface. So it's different than anywhere else. We would not have expected something like that on a body that, if the surface was really 4.5 billion years old and mixed and gardened over that period of time, to have something that coherent and that long on the surface. So it looks like that there's something that came out on the surface not too long ago, 100 million years, a billion years ago, and it's just surprising.
Okay, great. I see two hands. Let's take the one in the back first is who I saw first. I'm sorry. Is that Oz? No, it's Carl.
Appreciate it. The water on Vesta, based on morphology of the ridges, is there evidence from any spectral observations of alteration products on the surface of Vesta as well to support that?
What was the question?
Water on Vesta, is there any evidence from spectral measurements of alteration products to further bolster that hypothesis?
Okay, well, first of all, if you go back to the head meteorites, there's quartz in one of those meteorites, so there's that would require there to be a significant amount of water at one particular time when that rock was being formed. But we do have OH and H measurements with Grand and Veer, but they only look down, about that far.
Okay, and one more question, right in front. Would you please identify yourselves before you ask questions?
Mark Robbins.
There will not be retribution. It's okay to identify yourself.
I wasn't worried. You mentioned the high albedo of Vesta. Can you put a number on that or compare?
Well, 0.4 on the average, but there are albedos that go up to 0.8, and of course, then there's almost zero.
I assume that's normalized or normal albedo, or is that bond albedo?
Right. That, to the degree that the 0.4 is an accurate number, it doesn't matter. It's not.
That's really high, yeah.
Yeah, it is really high.
Okay.
Okay, in the interest of time, I think I'll have to cut off the questions at this point, but thank you very much for a very nice talk. And I have two announcements for you before we take our 10-minute break, but it will be a 10-minute break so that you can come back and hear Rick Elphick talk about barnstorming the moon. The first message is, if you have not signed up for your lunch and you want to eat lunch here today, please do so during the break. And the second is